You can start.
Hi, okay, so I'm going to start by, so today we're going to look at some interacting galaxies and nearby galaxies, and I'll take questions later on, okay? So let me start now. I hope you can hear me. And then I'll move on to the distance scale and measuring distances, which I said is going to be the most important thing in terms of figuring out the scale of the universe. Okay, so now, so I'll start by clarifying a very simple thing. It might seem very obvious to you, but it looked like some of you have confusion in this. So, I said in astronomy we use angular measures because that is independent of knowing the distance. Okay, so angular distance between two things, when I say distance between two things, I mean angular distance between two things most of the time, because I really don't know how far away they are, and so I can't measure the distance in kilometers or parsecs. So a distance between two things on the sky is a number of degrees or number of whatever. And then angular diameter of something or angular size is from one end to the other, the size and angle, the angle that subtends with me. Like the angular size of the moon is half a degree, right? So when I say the size of the moon, it most of the time means half a degree, right? Because to measure the actual size of something, you need this, right? And this, of course, everybody knows from school, but I wanted to iterate that the fact that the linear size of something, the linear separation between two things on the sky, is dependent on knowing the angle, which can be measured very easily. But then you also need this distance, right? And that distance is what I'm going to talk about later on, how to measure, and you will see it's not that easy. So this is why but if we know the angular size and we know the distance, then we can measure the linear size or the linear separation of two things. For example, if you have, say, I just pulled out a random number, on a certain day, Jupiter was so many million, now actually Jupiter is 700 million kilometers away from Earth. 10 years ago it was 20 years ago it was 600 million kilometers away from Earth. Angular, on that particular day, the angular size was 48.6 arc seconds. That's the symbol for arc seconds. Now, us astronomers, we use arc minutes, arc seconds, degrees all the time, and I forget, and a lot of us forget. You will find in this whole month that when people talk about distances, people actually think in real distances, right? And so you'll have to, in your head or somewhere, learn to convert these two things or these two concepts. So, for example, this number is very important. The fact that 1 radian is 180 divided by pi degrees, and that's so many arc seconds. 206,265 is a number that it's worth remembering. So we need the radian because in this particular formula, that angular size is in radians. You have to, so in order to use this formula, d equals alpha little d, you need that alpha to be in radians. And this is something even my students here forget much of the time. I mean, you give a test and people work out things and they forget that that number is in radians. So if you do that, you apply this formula, you can, from that size, you can find out that the actual size of Jupiter is 143,000 kilometers. Right? So this is how you apply this formula. And this applies to also not just the angular size of something, but the angular separation of two things. So there are two stars on the sky or two planets on the sky, whatever, and you want to find out how much they are apart, you have to know this distance. So that I wanted to clarify that, and I did talk about this in the beginning, but from the questions it looked like some of you have a confusion. Okay, so then let's get back to the local neighborhood of galaxies, and I complete that story before moving on to talking about distance measures and things like that. So as I said, the local group has our galaxy with lots of satellites, and then the Andromeda galaxy and lots of satellites around them, and they are both falling towards each other. Sorry, this is a better picture, and so then these lines actually, of course, don't exist. They are just to make sure that you understand the three-dimensional view of the thing. And here's Andromeda and our galaxy. And then, if you remember the two satellites I showed you in that picture taken behind the telescope in Chile, where you saw the Milky Way and you saw the two Magellanic Clouds. So these are the two Magellanic Clouds, and this is a very nice picture of our galaxy. It's actually a real image, but not taken from outside, taken from the vantage point of the sun, looking towards the center. But this one is taken in the infrared, and you can see the structure of our galaxy and the bulge, etc. But you can see the two nearest satellites, the large Magellanic Clouds, the small Magellanic Clouds. The large Magellanic Clouds, if you zoom in, it's a nice picture. It is an irregular galaxy with a bar in it, and it looks like you have scrambled an egg. It's very scrambled. These are small dwarf galaxies, are irregular galaxies. 30 Doradus is a very important nebula within that galaxy, in which there was a famous supernova in 1987, which is in our lifetime the nearest supernova that we've seen. We haven't had one in our galaxy in the last 300 years. The whole of the large Magellanic Clouds is much larger than the moon on the sky. It's about 3 degrees across on the sky, so it's pretty big, and you don't see it from, as I said, from India. You really have to go down below the equator to actually see it, and then you see it with the naked eye. It's up on the sky. Okay, and the small Magellanic Clouds is not smaller. That's a very famous globular cluster, which is in our galaxy. Now, what is happening is, if you look at the Magellanic Clouds, you see these, and then radio astronomers long ago found that actually, if you look at the gas, not the stars, then they are connected by a bridge. And I don't have a picture for you here. Connected by a bridge of gas. And that bridge goes all over the sky. And there was a lot of speculation in the 1970s, 1980s, when this was first discovered, what is actually happening. Then people realized that what is happening is that our galaxy is so big, and these are tiny galaxies which are orbiting around our galaxy. As they orbit, the tidal field of our galaxy, and remember, tidal means is the differential gravitational field. If you have, just like tides from the moon, if you have an extended object, then near you, then you are pulling the front, the bigger force, gravitational force, than the back, right? And as a result, there's a tidal force, which means that there's a differential force across this extended object. And this is why, for example, moons cause the tides in the ocean, because it pulls the near side of the water on the Earth with a higher force than the far side of the Earth, and tides occur. Similarly, tidal forces are very important in astronomy, because most objects interact gravitationally, and they're extended objects. Galaxies are extended objects. So the tidal force of our galaxy, when it acts on these dwarf galaxies, they are pulling out stars and gas out of these galaxies and slowly having them disintegrate. So as these galaxies are orbiting the big galaxy, they break up. They break up. First, they lose the gas, and then they lose the stars, and often they don't survive for very long. They fall into the galaxy, and the big galaxy kind of eats up the smaller galaxies. and grows. And so here is an example. The Magellanic Clouds are doing this, but recently we've discovered something called the Sagittarius Dwarf, which is even nearer than the Magellanic Clouds. And here's an example. These are the stars in the Sagittarius Dwarf, and this is what it looks like. It's actually detected 270 degrees across the sky, right, in stars. And it's one stream, and it's just positions of the stars in a galaxy, a small galaxy, which is like the slightly smaller than the small Magellanic Clouds, which has been completely broken up by the tidal field of our galaxy. And you can see the debris, and it's falling out, and it's about half the distance to the Magellanic Clouds. And it's been recently discovered because once the stars have been broken up, to recognize the fact that all these stars belong to the same stream falling in took a long time. And from the Sloan survey, this was first found about 20 years ago. And now it's been studied. So this is a common phenomenon of dwarf galaxies getting nearby in their orbit around big galaxies and falling in. This is one of the examples of interacting galaxies. Galaxies can eat each other. Then if you look at the other dwarf galaxies that are around us, they vary in their morphology. You can see there are bright ones like NGC 6822, IC 1613. They're all kind of scrambled galaxies, but they're substantially big enough that you can see them on the sky, bright enough. And so, for example, these galaxies are 10,000 times smaller than our galaxy. But if you look at 4NX Dwarf, for example, it's barely visible above the background, so very faint. And then you have, around other galaxies, you see the same thing. You see tidal dwarfs, dwarfs that are being broken up by these galaxies. Here's a good example. Our nearest big galaxy, the Andromeda Galaxy. And this is a very famous picture from long ago, taken with a small telescope. And you see M32, M31, M32, and NGC 205, just like our two Magellanic Clouds, the nearest two small galaxies near Andromeda. But recently, people have done very deep images of this. I mentioned Raja Guha Thakurta, who uses the Keck to observe the Andromeda Galaxy. This is one of his images. And you can see this is the center, and that's the galaxies near Andromeda, and you can see if you take a very deep image, you will see that these galaxies are connected by stellar streams. As of now, you don't see them in this picture with a small telescope, but with a very deep image, you can see that the big galaxy is actually grabbing stars from the small galaxy. You can see all this debris falling into the big galaxy, and in this debris, they have discovered all these little dwarf galaxies. See Andromeda 12, Andromeda 11, 13, 14, 16. These are all tiny dwarf galaxies that are satellites of the Andromeda Galaxy. Okay, so this is this part of the central bit of the Andromeda Galaxy. That and you can see that there is a big stellar stream coming through. So this is happening, and then along with all those dwarfs, the Andromeda Galaxy is falling towards us because we are gravitationally attracting each other. Even though the universe is expanding, our gravitational attraction between our galaxy and Andromeda is strong enough that it pulls Andromeda out of the cosmic expansion, and we are falling towards each other, right? And so, what is going to be the fate of these two? This is something I worked on for my PhD thesis long time ago, and one of the very first papers I wrote, we figured out that actually they are heading towards each other in a straight line, and they're going to collide in about 4 billion years. This is the last paragraph of the very first paper I wrote, which essentially says that the most of the inner part of the galaxy and M31 will actually collide with each other. They are not going like that. They're actually in a straight line orbit. And I'll show you a simulation that my friend made of this later on, where he actually quotes this in the film that the simulation shows. Dubinsky 2005. It's there on YouTube and on their site, and it'll show you what happens as these two galaxies, and they've simulated now. So these are the two galaxies um, um, shown as two disk galaxies. They're coming towards each other, and in 4 billion years they're going to come, and this is what's going to happen. Because they have some angular momentum, they're going to go past each other and then fall, and the whole thing will take about 1 billion years for the two things to merge. And remember, if this is our galaxy, our sun is somewhere here. Right? So this is a simulation in which they've taken care of the stars and the dark matter and the gas, and everything is in there. You see only the stars, and the simulation looks like this. Now you can ask, what can I trust this simulation? Is this true? And this is the best one we have so far. But in some cases, we can do the reverse. What we can do is look at the end product like this and try and see whether giving two disk galaxies and throwing them together and having the gravitational forces act between them, can they reproduce something like that? So here's an example of that. I'll come back to this in a minute. Example of that is the mice, very famous example of interacting galaxies, because they look like playing mice. These are two galaxies that are interacting with each other. You can see that as a result of their coming together and closely interacting, the tidal forces, etc., stars have come out of them. The question is, can you reconstruct this by looking at how two galaxies, these galaxies, can come together and collide with each other? This is something that people started doing a long time ago. And if you can look at, for example, here's a simulation of two galaxies, and you can play around with what the relative masses will be and the relative orientations will be, how far away it is, just to see whether you can reproduce something like the mice. And you can see how this will work. So as time goes, the two galaxies are coming together, and the tidal forces are going to distort the smaller galaxy into very interesting streams. The cores of the two galaxies will be more or less intact, but you can see the outer parts are going to go and become very, very distorted, and this looks very much like the picture you saw of the mice, right? So that's these are some of the best simulations that have been done on supercomputers. You take, because you have 10 to the power 8, 10 to the power 9 particles in here, which take part in the simulation, and you have to calculate the gravitational force between each pair and put some hydrodynamics in to simulate what the gas will do, etc., etc. And then you can produce something like this, and you can take this forward and say this is what the mice will look like in 1 billion years' time and stuff like that. So this is a very interesting game that you can play, and you can improve these models, right? So closely interacting galaxies, as I told you, the stars themselves don't collide because they are very tiny compared to the distance between them. So as very few stars will collide as the galaxies collide, but the various features you see because of because of the gas colliding, and actually the gas colliding could cause rapid star formation. There are very interesting examples where in interacting galaxies, star formation is very high, star formation rates are very high. A good example is this particular system, M81. If you look at the right picture, you can see the optical picture of M81, and nearby is this very tiny little dwarf galaxy called M82, and another galaxy here. But if you look in the radio, this is the left-hand plot, is the radio plot in 21 centimeters, and you can see how the gas is being exchanged between all these galaxies. They're interacting. You wouldn't see that in the optical picture. In the stars, it is hard to see what's happening in between them, but you can clearly see there's a lot of interaction going on between all three galaxies. If you look at the cold gas that emits radio emission, and that's a radio telescope picture. And this particular galaxy, M82, which is tiny here, is has one of the highest star formation rates in the universe that we know. It's a fantastic starburst galaxy, M82. That's a picture of it. And in the H alpha filter, which actually shows the amount of star formation that's going on. So Small galaxies, once they get into a situation in which the galaxies are interacting with each other, can become very bright because a lot of stars start forming and things like that. So, and later on, people will talk about star formation in galaxies and properties of galaxies. So this is something to keep in mind. Now, I know that there are hundreds of people here, and a lot of people are raising their hands. So I'm going to quickly take 2 questions and move on. Otherwise, if I take all the questions, it's going to take a very long time. So in sequence of the raised hands, let me see if Purvi can ask your question. I'm asking you to unmute.
Hello, good afternoon, sir.
Yes, go ahead.
Yes, I had a doubt about the dwarf galaxies that you mentioned, which say as like a satellite galaxy which surrounding the main galaxy. So, do the rings from the larger galaxy drive out the components of the dwarf galaxies? I mean, how does it hold together?
No, nothing drives out things. What happening is, I give the example of a tidal interaction, right? So what happens is that if you have a small galaxy that's approaching a big galaxy, the near part of the small galaxy is pulled by a higher force than the far part of that galaxy. So there's a differential, a df/dx, if you will, along the galaxy due to the force of the bigger galaxy, and as a result, things get pulled out of the galaxy. Right? Then and so this is why you have these streams that can be, so you can have the gas as and this is actually orbiting the big galaxy, right? As it orbits, it experiences loss of gas along the orbit towards the bigger galaxy, and this is but then it's also orbiting, so it is you can see the gas strewn around the path of the galaxy and things like that. So there are lots of these effects that one needs to study. That I've not gone into all the various effects of how a continuous medium like a gas or dust can be pulled out of galaxies by other big galaxies. But these are interesting things that you can study. But very intuitively, this is what's happening. Galaxy can be torn apart, its stars and its gas, by the tidal interaction with the big galaxies.
Okay, sir. Thank you, sir.
Right. So let's. I'll take one more question. Jerin Judy, I'm going to unmute you. Yes, go ahead. Ask your question.
Hello, sir.
Yes.
Yes, sir. What are the parameters on which we differentiate a galaxy and a satellite galaxy?
Mass, light, whatever you can measure. So, for example, a satellite galaxy is something that goes around a bigger galaxy, right? That's the definition. And you have 60 moons of Saturn that go around Saturn. You call them satellites, right? So it's a smaller galaxy. That's it. And smaller in what sense? If you can only measure the light, the luminosity, then it's from the luminosity. If you can measure its mass, then it's the mass. But a satellite is defined as something that goes around a bigger galaxy. Okay. A quick question from Junik. Unmute.
Hello, sir. Am I audible?
Yes.
Yeah. My question is, when suppose two galaxies, spiral galaxies, just like our own, which is rotating at a very high speed, suppose they collide on a 90-degree angle to each other, and the rings of one of those just directly collide to the central mass of the second one, will that cause any
There's
special
no ring
difference?
in a galaxy, right? First of all, you have the spiral arms in galaxies.
Yeah.
Now,
right.
actually, the massive part of the galaxy is the dark matter halo, which we will talk about later on. That's the main thing that matters when galaxies are colliding. The spiral arms, it turns out, are very small, maybe of the level of 1% or 2 enhancement on the density of the galaxies. They don't carry much mass. They are very visible because they have a lot of newly formed stars which form along the spiral arms, right? And that is why they stand out in brightness. But actually, those spiral arms don't have much mass in them. Okay, our sun goes through many spiral arms in its route around the galaxy. Not much difference. is felt by the Earth as they go around them. So it's not a question like somebody's hitting you on your head with a pipe or something like that. Don't think of it that way. That's why I showed you these simulations. In the simulations, you will see the galaxies collide head-on. It's the gas and the dark matter around the galaxies that make the difference. It's not the stellar features that you see. Okay. I hope that answers your question. I'm sorry, I'm going to have to move on with my talk. I'm not going to stop here because I'm going to move on to the next bit of the topic, and that is to do with distance measurement. And I'll come back again towards the end of today's session at 12:30 to see whether you have any questions. Okay, thanks. So let's move on, and I'm going to talk about. So I told you that we are here in the around the sun, in the galaxy, looking out in the universe, and one of the crucial things, even within the galaxy, to figure out what the three-dimensional structure is like, is for us to see what the distances to things are. So here is very important. Then the most important thing is what we call is the distance ladder, because what you have to do is you can't really measure directly distances to very far away things. You have to build up a ladder, which means you have to measure things to the nearby things and distance to nearby things, and then based on that you use that as a calibrator to measure distances to slightly far away things. So this is why it's called the cosmological distance ladder, or the distance ladder, because you build on the lowest rungs, and if there is in the lowest rungs have to be very strong, because if the lowest rungs have a error, that error propagates as you go across. Okay, so for example, here you are. So we divide this into phases, and the first phase is within the solar system, and then you look at the nearby stars. But measuring the distance to nearby stars, you have to depend on direct measures within the solar system. So fortunately now, with current technology, we can measure distances very directly within the solar system. Okay, and then based on that, you have geometrical methods to measure distances nearby stars, and then that propagates, and we'll come to all that today and tomorrow. So let's look at the first rung of the ladder, and because each rung of the ladder then gives you information about what's going to happen next. Okay, so first we must find out how big the Earth is, and you know that you've seen your students in your university who do geography or geology do these experiments where they have these theodolites or various things in which they measure. They have to draw a map of a terrain. And so they essentially use that small angle formula that I said, D equals alpha times small d. And they measure angles between things, and they measure distances, and they measure heights and things like that using these little telescopes, which allow you to measure angles, right? So this has been used for centuries to do surveys of the Earth and then measure angles. And now, of course, we have GPS. We have various satellite-aided things to measure things very accurately, angles very accurately. Okay. Now on the Earth, so the radius of the Earth was measured with shadows and things like that 2,000 years ago. I'm not going to go into all that. I'm looking at what the current measures are. So first of all, I'm assuming you know that you can measure survey the area of the Earth very well, and people have built very, very accurate maps. And now with technology from satellites, and GPS, Google Maps, GIS, our own ISRO has surveys that have maps that actually are accurate to about 60 or 70 centimeter resolution. Google Maps are even better than that, are going on to 30, 40 centimeter resolution. And so you can measure angular sizes on the Earth, and then look at the terrain and measure how the terrain varies, etc., very, very accurate. And also, the size of the Earth quite accurately. So then, to go into, then you, next stage in this ladder is trying to figure out how far the moon is, and how far the sun is, and how far the planets are. Yeah. So here, the current technology right now, we can do laser ranging. Okay, so we can actually bounce a laser off the moon, and from the travel time, we can find out how far away the moon is. And this is being done every minute, so that we know moon's orbit very, very accurately. Okay, so how do we do this? We have about 5 or so arrays on the moon that have been left there, and we have then laser ranging things. This is the one in the McDonald Observatory in Texas, in the US, where you have a laser that's actually pointed at the moon. So here are examples. I mean, in the 3 Apollo missions and 2 of the Soviet missions, 5 places arrays of mirrors were left on the moon. Okay, they look like this. Okay, so these are and so they are there, and there are people who routinely come and ask me, did we go to the moon? I mean, was it all filmed in some studio in Hollywood and stuff like that? I remember, growing up with many of my relatives believing that. Now, if somebody asks you that, you can actually say, look, you can actually see these things on the moon that man left there, and there are people who actually went there. So this is the Apollo 14 one, for example, in 1971. That's very, very useful. The Apollo 15 one, and they are left here. See, that's the Apollo 15 one there, Apollo 14 one. And if you remember the last Chandrayaan that went from India, which actually the lunar lander didn't work. The lander crashed. NASA had sent one of these with it, and because we were going very close to the South Pole, that was one of the things that we are going to leave there. So that actually broke, so we don't have access to it. But that was where Chandrayaan 2 was landing, right? The lander, and the 6th array would have been there operational by now if that lander had worked. So these are mirrors, and from which you can send the lasers from the Earth, which are in many places. These are good examples of the ones that were set out. The first 3 were set up in 1969. There many have been added to it, which from various places in the Earth, laser ranging. The one in Hawaii doesn't work anymore. They have their work divided, so they just shoot a laser and it comes back and you measure. And since you can time the arrival time of the laser very accurately, you can measure the distance to the moon in centimeters. And so this is being done routinely from 1969. Okay, so we now know the distance between the Earth and the moon, and the orbit of the moon around the Earth so accurately, right? Directly. How do you do for other planets? Venus, actually, we haven't gone to Venus, so we haven't. We have gone to Venus. There are things that you can't leave things on Venus, because Venus's surface is very, very hot, and so. But then we have used these large radar echo systems in which radio waves are bounced off the outer atmosphere, and they go inside and reach the surface and come back. This has been done for a long time. And so we can measure the distance to Venus. It's not optical lasers, but these are radio. And then, so from that, you can actually measure the distance to the sun. And this is how you do it. So here you are at the Earth, and you can measure the distance to Venus when it at its Venus is going around the sun, and it's inside the Earth's orbit. So it's you wait for the longest elongation, which means the greatest distance between Venus and the Earth. And if you catch that, then it's a right angled triangle. And if you measure this distance at that time by radar bouncing off Venus, then from this right angled triangle, you can measure this distance of the Sun, right? Because you know this angle, you can measure the distance of the Sun. And we know this now, sorry, this is wrapped around, we know this too about the astronomical unit, which is the distance between the Earth and the Sun, the center of the Earth and the center of the Sun, to about 30-meter accuracy, right, using this method. And so this is very important because the Sun-Earth, of course, this varies slightly because the Earth's orbit around it is slightly elliptical, as you know. And so this varies around the year. We talked about this yesterday, but the mean distance between the Earth and the Sun is this is the one that is defined by the International Astronomical Union, is the mean distance between the Earth and the Sun, and that is known very accurately. Okay. So that forms the basis of a lot of these distance measurements that we do in. And you find that this 30-meter accuracy doesn't matter that much if you want to, whether you want to have more of an accuracy in that measure, because you will soon get into uncertainties that are much bigger when you're using that as a calibration to go to the nearby stars. Okay, so to measure distances to the other planets, you can see even Pluto on this thing. You can, once you know the distance between the Earth and the Sun and the Earth and Venus, you can calibrate Kepler's third law on them. And Kepler's third law, as you know, is a relation between the period of a planet and its mean distance from the Sun. And of course, even you don't need to look at the mean distance. You can look at the semi-major axis of the elliptical orbit of the planet around the Sun, and that's what Kepler's laws gives you. Now, from Kepler's time, which was in the 16th century till now, the orbits of these planets have been measured. It's very you can accurately measure the position of a planet every day, every night, and build up the information about the orbits on the sky, and by simple geometry you can figure out what their orbit is like, and from that you can work out their distances. And even though, as I said, Pluto is no longer a planet and it has a very odd orbit because its orbit is kind of out of the plane of the solar system, it actually falls on this line because it's still orbiting the Sun, and so it obeys Kepler's laws, right? It actually obeys Kepler's laws because it has an elliptical orbit around the Sun with the Sun at the focus. So then we move on to how we use it for. So the next stage on this is the distance to the stars, and there what we do is we can't really shine a laser at a star and have it bounce back. In any case, the nearest star is just over a light year away, so that itself is an impediment. But of course, we haven't done anything like this yet. So what you do is you build on this basic system that I've just described, and then look at how you go beyond that. So the next step in this is to measure the distances to the stars. So here is what you do. You use a method called stellar parallax. And this is highly exaggerated, but it works on the principle that the further away a star is, and this really works on the very nearest stars. It doesn't work on even all stars in our galaxy. You'll see soon why. But it works on the principle that if you see the same star from two different directions, then the amount that the star shifts in from these two different directions depends on how far away it is. And you can do this experiment yourself. You can put your finger in front of you and look at it from one eye, close one eye, and look at it from the other eye, and you'll see that finger has shifted, right? Okay. Now you can put it very far away and do the same thing, and you will see it has shifted much less. And this is because your two eyes have a parallax, because they are separated and they are looking at it at the same thing from two different angles. And as a result, you have this parallax method. This is how your brain constructs a 3D image that you see around you, right? You are now looking out and you're looking at a three-dimensional world, and your brain is actually reconstructing this by taking the two images of your two eyes, and then from the difference between them, figuring out how far away each thing is, right? So the brain works on this parallax method. Now, for stellar parallax, what we do is that the Earth is going around the Sun at 1 AU, and this is why this distance measure is important. The one I just described of measuring the distance between the Earth and the Sun is very important. And so, since we know that 6 months apart, the Earth is very far, is the farthest away from the Sun, from when it was 6 months ago. So you measure essentially where stars are on the sky 6 months apart, and you try to figure out how the position on the sky has changed. And and so you can see that as the Earth moves around the Sun, the star also moves in a circle like that. And if it's very close, then it will actually move much further. Now, this is very exaggerated. There is no star that will actually move so much in the sky, as you will soon see. So this is why our distance measure in astronomy is called a parsec. A parsec is the distance at which a star has a parallax of a second of arc. And you remember when I talked about degrees and angular measures, etc., 60 arc minutes make a degree, 60 arc seconds make an arc minute, so 3,600 arc seconds make a degree, right? So you can calculate how many radians there are. I showed you that number, 206,625. So 1 arc second parallax is 1 parsec. Now remember, then if something is greater than a parsec away, its parallax is going to be smaller. Now, the nearest star to us is more than a parsec away, just a little bit more, right? It's about 4 light years away. So the nearest star has a parallax of 1 arc second. That's a very tiny angle. So this is why I'm saying, don't be fooled by this diagram in textbook, which actually shows stars going around. It's very hard to measure. But people have been measuring this from the 1850s, or even earlier, actually. So, so here it is. I've already talked about this. So measuring parallax is difficult. Parallax shifts are very small. If you look at 5 stars and this is, and look at the relative distances between them, you can barely make out that this is shifted a little, etc., etc. Parallax shifts are small; they're less than 1 arc second. I've already told you the atmosphere blurs images, and from cities like where I am sitting in Pune, the blurring of every stellar image, the seeing due to the atmosphere, is probably about 3 or 4 seconds of arc. So there is no way I can take a telescope here and measure the parallax of a star. It's impossible. The best places on the Earth have seeing on the best of nights of about 1/3 of a second of arc. But most observatories have of the order of a second of arc. So you can barely measure. And the way people have been doing this for 200 years from the Earth has been to do repeated measurement. As you know, from physics lab, the fact that if you repeat a measurement many times, then the errors of the measurement come down by square root of n if they're independent measurements. And so you can actually measure the accuracy. You can improve the accuracy of a measurement by doing something 1,000 times, 10,000 times. This is something that you can do. And so this is how parallax has been measured. Now, it is complicated by the fact that all stars are also moving in the galaxy. Now, then this is called proper motion. So proper motion complicates the issue. if, for example, the star itself has a motion, and you're trying to find how much it moves in 6 months, then the proper motion itself is going to affect the result. Thankfully, the proper motion is much smaller than the parallax that you'll measure, and in most cases, the proper motion is so small that it does not matter, but in many cases it does. So there are ways of decoupling the two. When you make repeated measurements, you fit a model that has the parallax, because you're not just measuring once in January and once in July. You're measuring the positions of certain stars continuously every night or every day, and then you have many points in which you can fit a model. Right now, doing this, for many decades, people have done this from the ground, and people can measure parallaxes to about 1/100th of a second of arc. Now, if you have 1/100th of a second of arc, that means you're going out to 100 parsecs. And within 100 parsecs, there are many stars. So you can do this, many thousands of stars within 100 parsecs. So you can do this for many stars by repeated measurement, then fitting a model in which you have a parallax and a proper motion. But it is very clear that in order to get any better than this, you cannot do it with a telescope on Earth. You have to go into space. Okay, just the basic calculation, you can see the distance in parsecs is 1 over the parallax, because the parallax is less if you go further away. The star Alpha Centauri, which is the nearest star, has a parallax of 0.76 arc seconds, because it's 1.3 parsecs away, about 4 and a bit light years. Say, for example, then another star that will have a parallax of 0.02 arc seconds, it will be 50 parsecs away. 0.01 is about 100 parsecs away. Okay, you can see here our nearest stars, and these circles are about 5 light years. I mean, this is a book that did not use parsecs, but you can see then this is 5 parsecs. This outer circle is 5 parsecs. So 5 parsecs would mean a parallax of 0.2 arc seconds. And that is about the best you can get with a single measurement with the largest telescope on the best site in Hawaii, Mauna Kea, for example, which is the best place to do high precision measurements. You can actually, if you can go out to even 5 parsecs, you have lots of stars nearby. These are all the nearby stars that you can see that are around the sun, solving the sun. But people have been doing this for a long time, and so we built up a whole database. And then the Hipparcos satellite went up. When I was a student, this was a big thing in the 1980s when Hipparcos went up. Hipparcos started doing parallax from space. And once you do parallax from space, 2 things happen. One is that you can actually measure distances, measure spacings, the angular distance much more accurately, because no atmospheric blurring. The other thing is you can continuously measure things. You don't have to wait during the day, because in space there is no day and night. And unless you are actually eclipsed by the Earth, which Hipparcos is actually a satellite that goes around the Earth, it could measure things to a very precision accuracy, but with longer periods of time. And it measured in its lifetime, it doesn't work anymore, in its lifetime of about 5 years or so, it measured parallax for about 100,000, a lakh stars, to 1 milliarc second. Remember, I said you can do up to about, maybe for repeated measurements, you can do up to about 0.01 arc seconds from the Earth, even though not very good. But Hipparcos did this for 1,000th of an arc second for many stars. And you can see, if you actually have orbits that look like that, and these are in milliarc seconds, you can fit a model in which you have the parallax and the proper motion at the same time. Very nice measurements, and the measurements are very accurate. These have error bars in them. You can see and Hipparchus changed our view of the distribution of nearby stars. And once you have parallax distances, that direct distance, not model dependent, these are geometrical. There is some model dependence because you have to take out the proper motion, but you can solve for these equations and take out the proper motion and parallax separately. And then for 100,000 stars near us, that gives us a very nice three-dimensional view of what our galaxy looks like. And this is when from Hipparchus is what we discovered, that the disk of our galaxy has two disks in it, a thick disk and a thin disk. This is how we discovered that the distribution of stars follows two exponential disks. We discovered that our disk has a warp in it. It's like bent and things like that in our galaxy. So Hipparchus brought out some really interesting features about the distribution of stars in our galaxy. Actually, I said superseded by Gaia to 2010. Gaia actually didn't go up till much later than 2010. This has now the big thing. Gaia is still working. It was launched in 2013. It's a huge Hipparchus. It is essentially measuring the distances to 1 billion stars. Talking of 10 to the power 5 stars here, this is doing 10 to the power 9 stars, okay, because it goes to much more accuracy than Hipparchus. It is measuring distances to 1% of all the stars in the Milky Way, right? And it also has not just an imaging system that measures accurate positions, but it has a radial velocity spectrometer that measures velocities of stars very accurately. Hipparchus also had something like that, but not very accurate. This actually does actually measure the distances by Doppler shifts, the velocities, and so it measures velocities and positions of stars continuously. And the interesting thing is that it just released the third data release a few months ago, which has already a billion objects. But the interesting thing is, it is Gaia is at the second Lagrangian point of the Earth-Sun system. I don't know whether you know that in any two-body system there are 5 Lagrangian points in which you can put something that's in a stable position. Lagrangian points are where the forces due to the various objects cancel out. So these are equilibrium positions. Some are unstable and some are stable equilibrium positions. You know that we are sending a mission. ISRO is sending a mission to observe the sun. It will be launched next year in January, called Aditya, and we are actually, for the first time, ISRO is planning something to go to L1, and it will be there in L1 so that it is not eclipsed by the sun. It will observe the sun 24 hours. This Gaia is in L2, and it has an orbit which is like this. It's a Lissajous figure orbit, and it's a repeated orbit, but it's very well measured, and it's so you can see what the advantage of this is. First of all, it is independent of an orbit around the Earth, right? Hipparchus goes around here. It's observing the stars away from the Earth, so there is no eclipse or no down period. 24 hours it can observe the stars. It is not dependent on the Earth. It's away from the Earth. Secondly, because it has a Lissajous orbit, it every time it comes back, it doesn't come back to the same point, and so it has a different direction from which it is looking at the stars. So it's an independent. It is an independent measure. So in this very complicated orbit, it can have many independent points of measure, and so as a result, it has built up this most amazing database of stars. And if you just if you have access to the archive or any published papers, you will see that some days after the data release of Gaia, the number of papers from Gaia go up, like 50, 60 papers a day, because people are doing Gaia hackathons, where they just take this, it's publicly available, all the data. And people can do all kinds of things. You can do, as I said, three-dimensional maps. You can look at, because you know distances, you can, and you have magnitudes, which means the brightness of stars. You can have the velocities. You can do all kinds of studies of different kinds of stars. This has changed galactic astronomy completely, because having precise measurements of distances are so important, because that tells you how bright a star is. If you're looking at stars, you can only measure the flux from the Earth. You don't know how far away it is, and so you don't know how bright it is. But once you know that, then you know how bright it is, how big it is, and then you can monitor these stars, you can model these stars and do all kinds of things. So you can pick up subpopulations of stars and look at how far away they are, how they're distributed, and things like very accurately. And if you can do this for all through the galaxy, at least away past the center of the galaxy onto the other side, then you have a very good idea of the distribution of stars in our galaxy. And so our knowledge of the Milky Way is evolving very fast now. Very, very fast now, because of Gaia. Because we are learning more about the distribution of stars and their nature just now. And so this is a good time to become an astronomer who can use this kind of data. Yeah. And already you can see that from the Earth, from the Sun, if this is the Milky Way galaxy, and that's 8 kiloparsecs, essentially it is covering all stars in this red circle, right? And for many bright stars, it can go out to the other side to about 20 kiloparsecs away. But out to 10 kiloparsecs, it is going to essentially, all the open clusters, the globular clusters, and things like that, it's going to find distances too. Okay, so I'm going to stop there. I can see many hands up and chat box, etc. So for today, I'm going to stop, and I'll see what questions there are and see whether. And please keep the questions relevant to what we've talked about today. Don't ask about black holes and things like that. I can see Ketan Singh's hand up. So Ketan, go ahead. I'm unmuting you.
Good afternoon, sir.
Yes.
Sir, my question is, when two galaxies collide or come closer, is there any probability that a planet or a star leaves its gravitational path and travel alone in a universe without having gravitational path?
Planet or star? Yes. What do you mean by a gravitational force? Yes, there are free stars moving around in space, within the interstellar space in galaxies. There are planets there. People have looked for interstellar planets, and they must be there. Certainly there are star streams, as I said, they're being pulled up, and they're moving in clusters of galaxies. In between galaxies, there are stars that are moving from one galaxy to another, or just free floating in space. It's possible. Nothing in the universe is free of gravitational force from anything else, because gravitational force is a long-range force. So it will be pulled by somebody or the other. But it is m1, m2 over r squared. So if it's very far away, the force is very small. And in its trajectory, if it comes very close to something else, it's going to be pulled by it. So it is possible, for example, due to this interaction, a star coming out of a galaxy and being pulled in by some other galaxy. Within the galaxy, this is happening all the time, that stars are moving and then it comes close to another star, gets captured and becomes a binary star. Yeah, and this absolutely happens all the time. So binaries are forming because one star is there, another star was passing by, and the gravitational force was strong enough. They formed a bond. They formed a binary system, gravitational bond, that is. So it not like electromagnetic bonds, but those are short-range forces. These are long-range forces. So binaries form in a different way. But this is happening all the time. Yes. Okay. Thanks. There's a question in the chat box that I'm looking at. Prometheus has asked, can one Lagrangian point hold two observatories? Oh, yeah, absolutely. James Webb is going to go to L2. L2 already has Planck. In fact, Planck and Gaia went on the same spacecraft and was dropped there. So they've been Planck observing the cosmic microwave background, and absolutely they can. I mean, think of the number of satellites there are in space. Space is empty. Elon Musk is throwing out hundreds of satellites every day, small ones, and they're all orbiting the Earth. So which is a pain for astronomers, because soon the sky is going to be full of these things. But yes, there is a lot of space, and particularly their orbits should be well defined. We know their orbits very well, so that they don't collide with each other, and those things are done. So yes, each of these hold quite a lot. Okay. No, and all satellites. Anand Menon has asked, do all satellites follow the Lissajous orbit? No, actually, orbits are normal elliptical orbits. Gaia was put on a very special orbit because there is an advantage of having such an orbit, because it allows the difference from orbit to orbit. You get independent measurements of parallax, because it is in a different point every time. Things like that. So that is why Gaia was put on such an orbit. But normally you don't need to do that. It's very complicated. Okay, so in the participant section, I can see Shorab Pal's hand up. Shorab, go ahead. Unmuted you.
Yes, sir.
Yeah.
Am I audible?
Yes.
Sir, I have a question from the first part. When two galaxies collided each other, so I want to ask, when an astronomer look at a new galaxy, is there any evidence left from which you can determine that these galaxies has collided earlier with?
Yeah, absolutely. Well, first of all, there can be direct evidence. For example, where you can actually see the debris. Like I showed you the picture of Sagittarius, where you can see the debris, the fact that it's being pulled and destroyed in the process of being destroyed. I showed you a picture of the mice, which actually you can see. I mean, you can go ahead, just Google and look at pictures of interacting galaxies. You'll convince yourself that these are galaxies in the process of interaction. But there are also circumstantial evidence that you can have. If you know what happens when two galaxies collide or interact with each other, often what happens is that the supermassive black hole in the middle of a galaxy gets turned on and becomes an active galaxy. And you'll hear later about active galactic nuclei and things like that. That often results from an interaction between two galaxies. And if you see something that's going on, or you can have a starburst going on, a huge, massive starburst like the M82. Even if I didn't know that it was near M81, a starburst like M82, which is forming 40 suns a year, 40 times as much as our own galaxy, which is 100 times bigger, is doing, I could have guessed that it has just had a close interaction with some big galaxy, because that is one of the mechanisms. So there's circumstantial evidence and there's direct evidence. Both you have. Okay. Right. Let's go to Shreya Sigatia.
Good
Yes.
afternoon, sir.
Yeah.
Sir, I was asking that this collision of galaxy can be regarded as a consequence of expansion of universe, like the fact that the universe is expanding. We have studied. So, can it be regarded as a consequence of that?
Just the opposite. No, absolutely not. In fact, the collision of galaxies and the interaction between galaxies happens due to the gravitational interaction between them. The universe is expanding is a completely different thing. It has nothing to do with gravitational force between things. In fact, our galaxy is going to collide with Andromeda in spite of the fact that the universe is expanding, not because of the universe is expanding. The universe expanding is taking all galaxies away from each other. So if we let all the galaxies flow with the universe and there was no gravitation, all the galaxies would have gotten farther and farther and farther away from each other. And I'll talk a little bit about the Hubble expansion later on, and we'll get more in the cosmology lectures. And that is because the space itself is expanding as a result of how the universe expanding from the Big Bang. No gravitation there. The space itself is expanding. Now, on space, in space, you have these galaxies and they're free to move. And how are they moving? So, if galaxies were fixed, like sewn together with thread on the fabric of the universe, then we would have just moved away from each other and done nothing. But the galaxies are not like that. Galaxies are free to move. And they are pulling each other. Everybody's pulling each other. So if I have a galaxy nearby, we'll move on this. So our motion with respect to a galaxy has two components. One is the expansion of the universe, and one is the pull due to the expansion, the pull of the two galaxies due to gravitation, and that's towards each other. If both cancel out, then we stay still. If our pull is more than the expansion of the universe, then it's coming towards me. And for most cases, our pull, another galaxy is not strong enough, and so it's going away from me. Okay. So for our dwarf galaxy satellites, the pull of the Milky Way is much, much stronger than anybody else's. So they're all orbiting us. Andromeda, and there are some other galaxies which also we are pulling strong enough that they are falling towards us and not going away from us. Right? M33 is another one. Then there are galaxies within the local group that are bound to us, just outside the local group, things like that. So think about it that way, that there is one push that is due to the expansion of the universe, and then there's a pull due to the gravitation.
Okay, sir.
Kaushik Manjo, go ahead.
Hello, good news,
Yes.
sir.
Go ahead. Yes.
Am I audible?
Yeah.
Yeah, thank you, sir. Sir, my question is when two galaxies are getting merged or getting collided, what happens to the central black holes of individual galaxies?
Very good question. Central black holes will merge into a big black hole. We have good pictures of 2 or 3 such systems. Let's see. Next time I'll bring around some pictures just to show you, because you can actually detect supermassive black holes by the X-ray gas around them. And so by the Chandra satellite, we have taken pictures of 2 black holes in the middle of a galaxy. They're not supposed to be there, so it just shows that there are 2 galaxies. And if you take a deep image of the galaxy, you can see 2 galaxies there, and they're in the process of merging, and you can see 2 black holes are coming close together. And so they will merge, just like in the LIGO detections. You see black holes merging to form a bigger black hole, but those are stellar mass black holes. We can't detect supermassive black holes through LIGO yet, because that's a very high frequency measurement. But these supermassive black holes will merge into a bigger black hole. So that's going to happen.
Okay, thank you, sir. I have another question, sir.
Very quickly. There are many other hands.
Yes. So when these 2 black holes are getting merged, and if suppose these 2 black holes are getting merged also, so does the density of the galaxy is getting increased or decreased, or the size of the galaxy is getting larger?
No, because the mass will get larger. I can't say anything about the size or density because it will depend on how it's going to, what the end product will be like. It's a very complicated method, right? You saw those simulations. So it can become a very diffuse galaxy after merger, and so the density won't. But the mass will increase, of course, because the mass is conserved. Right? You put 2 galaxies together, the resultant is the sum of the 2 galaxies. What the resultant galaxy will look like depends on how they are merging, the geometry, etc. We now think that the elliptical galaxies, you learn about this in your galaxy lectures, are formed from spiral galaxies merging together. Many spiral galaxies merge together. The angular momentum is destroyed because the angular momentum is a vector, and as a result, in general, if you have 2 things that have 2 different angular momentums, they add to form a small angular momentum. And if the angular momentum decreases, then the galaxy puffs up. It is less like a disk and more like an ellipsoid. And slowly, as galaxies merge, they become rounder and rounder objects, non-rotating objects, elliptical galaxies. So the morphology of the galaxy changes. Okay, that's what happens. So let me go to some of the questions that I see in the chat box. I have here. Let's see quickly. There's Kunal Shukla has asked, has India sent any telescopes to space like Gaia and Hubble? Of course. Right now, The Indian telescope in space is AstroSat, which was launched in 2015. It has 5 telescopes, the ultraviolet telescope, and the others are X-ray telescopes. They are producing amazing results. They are not Gaia. They have not been sent up to measure parallaxes, but they have X-ray telescopes, and so yeah. The ultraviolet telescope that's on AstroSat is the best ultraviolet telescope in the world. It's much better than any of NASA's telescopes. So you can read up on AstroSat, and somebody might give you lectures on AstroSat in this series. Ishika Chand asks, sir, any Lagrangian points? Can there be numerous paths? So I've already answered that question. Ritika Ghosh is asking, what is the use of Lagrangian points? From the picture you showed, I understand, is behind the sun. No. There are 5 Lagrangian points in any binary system. Please go and look up such things. If you have 2 things that are massive, and there are these 5 points where the force from the 2 cancel, right? Remember, there's also the centrifugal force of something moving around one of the objects. Okay, so the gravitational force from the 2 massive objects on this particular thing plus the centrifugal force, they cancel at 5 places, and these are the 5 Lagrangian points. So if you put something there at a Lagrangian point, it is in equilibrium. Okay, and that is why they are very good for parking or satellites. Okay, now I'll go back to the participants box. Your hands up, Anik Srivastav.
Yes, sir. Good afternoon, sir.
Right.
So my question is that you have described the different kind of galaxies. So what galaxies are more abundant in the universe, and if they are, what may be the chance? What may be the cause?
Right. You will learn about this in the galaxies talk a lot more. But as I told you, if you look at the different kinds of galaxies, the ellipsoidal galaxies are about 15 to 20% of all galaxies. But 75% of all galaxies are the disk spiral galaxies. Those are the things that are formed first. As a cloud collapses to form a galaxy, like our galaxy, it forms a disk because they are rapidly rotating. Now these disk galaxies merge to form the elliptical galaxies, as I just said. So the elliptical galaxies are rarer. They're often found in places where the galaxy density is very high, like in the middle of clusters. Later on, I will give you 2 talks in the 3rd week on clusters of galaxies after you've had galaxies lectures, and I'll talk more about it then. Okay?
Okay. Thank you.
Astha Chaturvedi. I'm asking you to unmute. Go ahead.
Audible?
Yes, you are.
Yes, sir. So, sir, when we were talking about the laser reflecting from the surface of moon, amongst all kinds of energy, how do we detect that this is the laser that has been found?
Well, that's the great thing about lasers, right? Lasers are they are monochromatic. They are exactly at one wavelength, very, very thin wavelength spread, and they're very bright as a result. And so if you shine a laser, it goes very far away. You can see it very far away. And because they're monochromatic, if you put a filter, it actually selects only one very small range of wavelengths, and it eliminates all the other kinds of light, right?
Okay.
And as it goes and comes back, due to it might move a little in wavelength because of the Doppler shift, etc., but it's within a certain wavelength range. So lasers are very good at this. Now, you can do this with the moon. You can't do this with another star or something like that. That's too far away, because of course the power of the laser falls off as it goes further and further away. But even with 1960s technology, you could do this with lasers and the moon. So that's very easy. Okay, Neil Badudaria. Go ahead, Neil. Neil, ask your question. Are you there? Okay, I can't hear you. So I'll go to the next one. Jyotirmoy Pramanik. Jyotirmoy, are you there?
Yes. Sir,
Yeah.
am I audible?
Yes.
Sir, my question is, if we assume several concentric spheres along the cosmological ladder, is it possible that many stars will be located on the same line of sight of the observer? Then how we remove this difficulty when we like to observe the distant star from the observer?
Right. I don't understand, because you're measuring the distance, right? So you can directly measure the distance by looking at their parallax. So if you are repeatedly measuring something, if something, same line of sight, if something is further away than another one, they will not move as much as the nearby one, right? So soon they will be out of line. You're measuring things over many years. So Gaia started in 2013, it's still measuring, right? In 7 years, this because some stars are, and it also has a very complicated orbit, Gaia, so it's looking at it from different angles. So you can easily separate out, even if the 3 stars on a straight line, you can separate out by looking at it from different angles. That's not a problem at all. And stars also, you're not just measuring the position of the star, you're measuring their brightness, their color, their everything, all other properties. So you can actually differentiate between the stars very well. Yeah, not all stars are not identical systems. Right? Okay. Now let's go down, and I'll take a couple of more questions. Vasudev is next. Vasudev, are you there? I've just.
Good afternoon, sir.
Yeah. Yes, go ahead. Ask your question.
When the galaxies collide.
When the galaxies collide?
What about the times? Which time the galaxies collide?
Oh, acha, you're saying when? I don't understand what you're saying. Galaxies collide when they come very close to each other. And if you're asking how long it takes for this whole thing to happen, it depends on the galaxy, it depends on how far away they are. But the whole process that you saw I showed in the movie, that whole process could take 10 to the power 7, 10 to the power 8, 10 to the power 9 years. Right? I told you that we are going to collide with our neighboring galaxy in 4 billion years. That's in about 4 times 10 to the power 9 years from now. So that is the kind of system. You're not like you're sitting here and you're looking at galaxies colliding. That's not going to happen. It takes 10 to the power 9 years. Okay, and that's the kind of time scale, giga years, in which you're looking at galaxy motions. The movie I showed you is pretty speeded up. Okay, and so I'm going to take a couple more questions from the chat box. And see. So Neil I couldn't hear him, but his question is that how do we account for the motion of the sun and the solar system in turn while using the parallax method? A very good question, and this is why I told you that we are the first rung of the ladder is that you have to look at, you have to know the Earth's motion around the sun. That is very well done, very well known, because we know the distance to the sun, and we know exactly where we are with respect to the sun. Our orbit around the sun is very, very well known. In fact, it's programmed into all our astronomical software. I use my standard astronomical software, and I'm actually looking at the redshift of a star or something like that, and I just apply the correction due to where the Earth was around the sun and the distance, etc. And those orbital elements are known. I don't have to do it by hand anymore. No, we know it. So that is very well known, as I said, because we know our orbit around the sun very accurately, and the moon's orbit around us and stuff like that. Those are known very accurately, but those have to be known in order for you to make this measurement of the next rung of the ladder. Okay? Rashmita Panda is asking what will happen to the planets in our galaxy if our galaxy collides with another galaxy. I'm sure you're very afraid what's going to happen to the Earth when our galaxy collides with Andromeda 4 billion years from now. I'm not sure humans are going to live another 100 or 200 years at this rate. So I'm not sure that is a relevant question. But I told you that as galaxies collide, the stars don't collide. And the stars the probability of two stars colliding is very, very small because the size of stars and the distance between stars, the size of stars is very small compared to distance between stars. So stars don't collide, whereas galaxies might collide. And if you're talking of planets, the size of planets compared to the distance between planets and stars is even larger. So actually two planets colliding is going to be a very, very a rare event. It's not that they don't happen. You can see stars merging with each other in the LIGO events, for example, but they are very rare. And planets colliding will also be very, very rare. Okay. Now there are hundreds of questions here, and I'm not going to be able to cover all of these. But let me see whether Deepa, your last question, asked to unmute. Deepa, I've just unmuted you. Go ahead and ask your question. I can't hear you. Okay, let's move on to Kunal Shukla. I've just unmuted you. Kunal Shukla, go ahead.
Good afternoon, sir. Sir, am I audible?
Yes, you are.
Yes, sir. First of all, thanks a lot for this inspiring lectures. Sir, my question is, how do we measure the distances which are so far, like millions of light years away? The distances of galaxies which are so far away.
Yeah, but that's exactly what I'm explaining to you, right? I haven't gone to that part of the ladder yet. I've just talked about parsecs, which is light years. So when I come back tomorrow, I'm going to talk about the thousands of light years and the millions of light years. Okay, I've just taken you to the nearest stars. Just wait. Okay, I'll talk about it. Okay, thank you very much. Until tomorrow, keep on asking questions, and I don't know whether Dipanjan has already set up this system of putting in your questions. Please do that, and I will see you again tomorrow, same time. Bye for now. Thank you for being here.